Okay, so I'll be talking about the UDF, UDA, and some things that we're going to build on top of them. The presentation is going to be in two parts. The first part is going to be about the UDF and UDA functionality, which is similar to what Cassandra already provides and similar to what other databases provide. And the later parts are going to be more interesting, but they're also in flux, so don't start writing your code based on that. It's going to change. This is just some ideas that we are going to implement. So I copy-pasted my bio slide from the previous presentation. So let's start with UDF, user-defined functions. So this is the way for you to extend the functionality of the database by injecting your code into the server, and the server will run it for you. The idea is that the code runs close to the data, so you don't need to move data around too much, and you can, if you run the code where the data is, efficiency is increased. Less network traffic, less data movement. So let's look at one user-defined function. Let's walk through an example and see what it does. So the first line is that you just declare a function. So you create a function, and you declare the name of the function. Here, the name is word count, because we're doing something simple. And you declare the parameter and its data type. Databases are strong on nulls, so you have to say what happens if you receive a null input. You might want to process the null and do something special with it, but usually a null means that there is no data for that particular record, so you can just skip it and the entire function will return null. Like most languages that are strongly typed, you have to also declare the return type of the function. So here we are counting the number of words in the line of text, and that number is an integer. And the language that we chose to implement for user-defined functions is Lua, and I will explain why later. And lastly, as everyone knows, if you want to count the number of words in the line of text in Lua, you go to Stack Overflow and you copy-paste the first. Everyone does that. That's, so here the syntax is a little bit special because it's using regular expressions, but in general, Lua is a nice and simple language. So after we created this function, we executed that statement. It gets replicated all over the cluster, and now the cluster knows about that function. It can use it like any regular built-in function. So here is an example. We're selecting, say, a partition ID, a field that has some words in it, and we're also selecting a function on that field. And you're selecting from a particular table. And you can also use this user-defined function in the where clause, which is the more interesting use case, because here you can actually tell the database to process the data early and return less data than it would otherwise. You might have run the word count function in the selection list on the client. It's just as easy, but doing the filtering allows it to return less data. So why did we choose Lua? So Lua really is built for this task. It's a very simple language, very easy to learn, and very easy to cut and paste from Stack Overflow. It has a small footprint, so it doesn't start grabbing gigabytes of memory. It allows you, because it is designed for embedding, it allows you to control the execution. So one thing is limited memory allocation, so you won't have a user-defined function starting to allocate tons of memory, and then the database runs out of memory and crashes. So we can configure how much we allow a user-defined function to allocate. And it also allows us to limit the execution time. And that is important for two reasons, and we use it in two different ways. One way is to prevent things like an infinite loop from blocking up a thread, and the database, you never hear from that thread again, or just taking a huge amount of time, and then other things don't work. But also, we can time slice the execution. Scylla, like we told you many times over this summit, has the feature can run multiple workloads concurrently, and you don't want some workload that is running a user-defined function starting to impact latency over a different workload that is running concurrently. So what we will do is we will detect if a user-defined function is taking too much time, still below its maximum allowance, but it is taking too much time, and then we will halt its execution, switch over to a different workload, run that workload for a while, and then switch back. And so if a function takes 20 milliseconds, that's not a huge amount of time, but it's still something that can impact your latency. So we will time slice the execution of this function, intersperse other reads and writes with it, and this way the latency doesn't go out of control. It's really easy to call from Scylla to Lua and back. It's designed for this switches. That's maybe not very important to you. It's also not very important to me because I wasn't the one who implemented this functionality, but it was important to Raphael, the ability to do these calls back and forth from the database to the function and back. And there is also a just-in-time package that allows us to compile Lua code and thus improve its performance. Even the interpreted version is not very slow. Of course, you wouldn't want to write very complex functions in it, but with a just-in-time functionality, it's even faster. Another reason is that it's not Java. Now, I don't want to be perceived as a Java hater, even though maybe I am. But Java has its place. It's easy to write code in it. It's a safe language. So it has its advantages, but it is not good for embedding. So it has a very large footprint. It starts by allocating gigabytes of heap, and the runtime itself is quite heavyweight, allocates a large number of threads for garbage collection. It's not easy to limit function execution time, like I said before, about if you code an infinite loop, you need some way to break out of it, and you also want to time slice execution. So it's not impossible to do it, but it takes work. You need to do some kind of bytecode manipulation, inject checks everywhere for that. And this comes with Lua for free. And with Java, we would have to work quite a lot for it. And it's also hard to integrate with a database. I don't know how many of you have experience with JNI, but it is quite complex and also quite expensive. So every time you need to pass data from the database to the user-defined function or in the other direction, this is going to incur some overhead. So use cases for user-defined functions. So you can extend built-in functions. Scylla right now comes with a very limited set of functions. We are going to extend it, but we cannot cater to everyone. There's always going to be one more thing that you want to do. And this allows you to do that. And you can put the user-defined functions in many places. One place that we saw is in the selection list. This is not very exciting, so it can allow the database to perform the computation, but you might have just as well performed the calculation on the client. But there are places that you can put it, such as the where clause, where it really brings value, because it allows us to filter the data in the database, and therefore save on network traffic, save on data movement, and this can really improve your performance. It can also be an input to an index. So I think this feature is not yet enabled, but we already have all of the infrastructure for it, so you can expect it to arrive. And that is, you can build an index, not just on a field, but on a field as transformed by a function. And this allows you to have many different indexes and different ways of accessing your data. So for example, maybe not a very good example, but you can create an index that allows you to select all of the records that have exactly 11 words in their words field. Maybe someone can come up with a better example. All right, let's move on to user-defined aggregates, which are an extension. So in the same way that we have functions in Scylla that take an input and transform it, there are also aggregate functions that take a sequence of values that come from different records and perform some aggregation, such as a sum or average, or count. So the input comes from many rows, and you return just one row at the end. So to build a user-defined aggregate, you have multiple components. So we are not going to pass all of the rows to the user-defined aggregate at once, because there might be millions of rows. We don't want to hold them in memory. So instead, we will define an accumulator, which is a kind of state that is held between rows. And each time, we will pass the current row to the aggregator, and it will update the accumulator. We will need an initial value for the accumulator, because there might be no rows. You need to start from somewhere. And there will be a row function, and the row function takes the current rows that the database is currently looking at. It takes also the accumulator, updates the accumulator, and returns it again. And this allows us to perform the aggregation. And finally, we will have a final function that takes the accumulator and transform it to the actual values that is needed to return, because the accumulator might hold more data than is actually needed. So let's look at an example. We will start with the row function. So the row function accepts two parameters. The first parameter is the accumulator, which represents all of the rows that we already processed. And the second parameter is the value we are aggregating. And this comes from the current row. So what we're going to do is we're going to mix the values that we just read from the current row into the accumulator. Again, we have to say what we want to do if the input is null. And the easiest thing is to just declare that we return null in that case. We can also say that we want to process the null, and then we'll have some if then else in order to check whether we actually have a null or not. And one interesting point is that the accumulator can be a tuple, or it can be a more complex data type, and it doesn't have to be just a simple scalar. So usually you return the same, well, always you have to return the same data type as an accumulator, because this function will be called repeatedly. It will start with the initial value, and then will be called repeatedly for every row. Again, we use the Lua language, because that's the only thing we support. And let's look at what the row function does. So it will, we receive the tuple in the accumulator, and we're returning another tuple. And what we see is that we increment the first element of the tuple, and we sum the input value into the second element. So what we have is a running count of the number of rows that we observed, and a running sum of all of the values that we read. Let's look at the final function. So again, we accept the accumulator. We processed all of the rows already. The database reached the end of the partition or the end of the group, and it wants to return a value. So it just gives us the accumulator. Again, we return null on null input. And this time, we return a double. So we can change the data types as the flow progresses. And here, we return the second element of the accumulator, which, if you remember, is the sum of all of the values that we read, divided by the number of rows in the first element. And the result is the average. So we re-implemented the average function. Not very exciting, but an easy-to-follow example. So let's put all of the components together. We create an aggregate with the create aggregate statement, and that broadcasts the new function to the rest of the cluster. We pass it the row function by name. It's called, the keyword for that is sfunc for state function. We tell the database what the type of the state variable is, our accumulator, and we tell it how to transform the accumulator into the values that will be seen by the client. And we have to specify the initial values for the accumulator, which in this case is 0, 0 for 0 rows already read and 0 values already summed. So what are the possibilities for user-defined aggregates? So top K calculations, you want like the top 5 records within a row, and you might have like some kind of scoring mechanism, so you don't want just the maximum or you might want to apply some transformation to the row and create a score, and from that you will find the maximum or the top 5 rows. There are many obscure statistics functions that we might not implement in Scylla, so you can implement them in a user-defined aggregate. And, well, I think I mentioned the last already. So some tricks that you can use with user-defined aggregates. We already saw that you can store a tuple. You can pass a tuple as an accumulator. That allows you to have multiple scalars and not just one. But you can also have a more flexible type, like a map or a set, so that you can have an accumulator that has a variable number of values that you can then manage. And you can also use the list data type in order to return more than one value from a function. All right, that was the first part, which is really feature parity with Cassandra and something that is available in many other databases as well. But now we will look at some things that we are planning to build on top of user-defined functions and aggregates. All right, so we have some enhancements, that feature requests from users and customers that we frequently hear. And we would like to find some way to satisfy all of them, but without implementing lots of little features, instead having some kind of larger feature that can satisfy all of them, even though they are quite different. So many users ask us for hooks into the compaction process. They want to transform the data as it is compacted. And we understand why they want that. This is a place where we see more of the data rather than just on ingestion. So you see the existing values as well. But it is also quite limited, because during compaction, you're not guaranteed to see all of the SS tables that contain a particular row. This only happens on major compaction. And major compaction is something that is very infrequent. In fact, on many clusters, it never happens. But we understand the reason why they want to hook into the compaction process. Many users have large partitions that can grow out of bounds due to some kind of malfunctions in the input process. And of course, that can ruin your whole day. So they ask us for a way to limit a partition to n rows, where this is something they specify, or perhaps or depending on some other condition. Something else that people ask us for is to be able to adjust the TTL, the time to live of a row. So they specify the TTL of a week, and now they want it to be gone in a month, not in a week. And right now, it's not possible to do that with Scylla. The TTL is deeply tied into the value itself. So right now, there's simply no solution for that, apart from just not using TTLs at all and issuing deletes from outside. And lastly, people want to do transformations to entire tables. And what people use now is things like Spark. But Spark lives outside the cluster. It can do a full scan of the entire table, move all of the data, perform some transformation, and write the data back. And that works great, except that we're doing a huge amount of data movement, and you have to stand up a new cluster. And we would like to provide a way to do that within the database without all of that data movement. So let's see what we can do in order to satisfy all of those requests with one unified mechanism. OK, so what people do now, I described Spark, but people also do roll-up handwritten code. And there is this blog post I wrote a million years ago about how to do full table scans. And that involves standing up a cluster of workers and then dividing the token range into subranges and issuing read queries in parallel and collecting all of the data back. And that is a lot of effort to implement. And we would like to provide a way that doesn't require all of that effort, sometimes it's worth it, but sometimes you really want a simpler solution. So like I said, data movement, more machines, and more work to code it. So what's the new approach? So just let the database read that blog post and have it perform those full table scans. It wasn't that funny. OK, thank you. So we already have a cluster. The cluster already has all of those schedulers that can run things on every shard and on every node. So we would just add that functionality to the nodes and perform that full table scan. But of course, when you do the full table scan yourself, you have your own customized code that does what you want, and the database doesn't have that. So this is where UDF and UDA come in. It allows you to customize the scans that the database will perform. So instead of replicating that full scan code in your custom code, we code that just once and within the database and push that custom code into the database. So some examples of how we can use that. We can issue, we also extend UDF and UDA to be able to perform more operations. So they're no longer pure functions. They can also perform operations. So it's more of a user-defined procedure rather than a user-defined functions. So we can tell the function to perform a delete. And that allows you to trim a large partition. So you're scanning a partition, you hit a certain size or some other condition that you decided upon. And when you decide that you've had enough, you just issue a delete to trim the rest of that partition. And you can also use that to implement a custom TTL. So you might have some extra record that tells you when you plan to delete that partition. And you can update that record. So if you want to change the TTL, instead of using the standard Scylla TTL means, you just update that record. And say once a day, you run a full scan that scans this TTL field and issues a delete whenever it sees that a partition is, a record is outdated, either a row or an entire partition. We can also teach the user-defined procedure to perform an insert. And that allows you to do a transform. So similar to a map reduce, you read some data, and you do some transformations on the data, and you insert it to a different table, which might be a temporary table or a permanent table. So this is all work in progress. Don't rely on that. So some examples. So here is a syntax for deleting rows. You select the primary key and the clustering from the table. You do a group by. And that means that the procedure will be executed once per partition key, and not once per row. And here is a trim procedure. And what that procedure does, it defines a local variable called counter, which counts the number of rows. And each time we see a row, we will increment the counter. And when the counter exceeds some kind of threshold, we will issue a delete. And once that partition ends and we move on to the next partition, because we had this group by in the previous slide, then the procedure will reinitialize and the counter will be reset to 0. So this is a way to force a procedure to run on one partition at a time. Here's another example. So we can execute a procedure called do insert now. And we only do that if the value satisfies a certain condition. So we can select the values that exceed a certain threshold, and maybe we move them to a different table in order to be examined later. And here is how the procedure looks. This one is really simple. We simply call execute with the prepared statement and all of the data. So here the database did most of the work for us, and the procedure is really simple because we did most of the work in the where clause. OK, let's talk a little bit about the implementation. Right now, there is no implementation, but this is how we see it. You should all be familiar with this picture that has the client talking to a coordinator, which in turn talks to the replicas. And for each partition, the coordinator and the replicas will be different, but this is representative. So what we do now is we add another level of coordination. So we can call that new level the aggregator. So the client will be issuing a call to the aggregator, and the aggregator will be issuing calls to every node and every shard, and each of them will coordinate just for that particular shard. So this is the place where we're running all of the queries in parallel. And then each coordinator will talk to the replica in order to do reconciliation. Of course, for full scans, you might want to run with consistency level 1, and in that case, we will not talk to any replicas because each coordinator is also its own replica. And that gives you a nice performance boost. But sometimes you do need that extra consistency, and you can choose the consistency level of quorum. It all depends on your use case. So performance considerations, Shlomi also talked about it. Full scans have a bad reputation of being slow or being inefficient, but they're actually very efficient. They're very efficient at moving large amounts of data, and if you need those large amounts of data, then they're pretty fast. The reason is that they're efficient is that every byte of data that they access is important to them. When you're doing a random read, you will issue a read, say, for a 4K block, and then you will extract a 300-byte record and throw away everything else. So you wasted above 3K, 3.7K of the data from the 4K you read. And that means that if you have, even if you're throwing a large fraction of the records that you're reading from a full scan, it's still pretty efficient compared to random reads. And Shlomi's talk really explained that well. And because the full scans, they're not only efficient, they're also able to consume data very quickly. And this is because disks are very good at providing sequential data. So you can, even if you scan at just 1 gigabyte per second, that translates to 86 terabytes per day. And that's per node. So if you have a larger cluster, you can easily scan petabytes of data per day. It's very easy to run these in fully parallel mode. So you can have all of your nodes running those computations and all of the shards running those computations. We know from people are often surprised that they see that that Scylla takes all of the CPU, so it's running at 100% CPU. If you have lots of shards, like 4,800% CPU or even more, people say, is that wrong? We say, no, it's wrong if it's below that. You want your CPU to be working for you. And of course, there is a risk with this efficiency. Because full scans can slurp large amounts of data, they also slurp the CPU and they slurp the disk bandwidth. And this is where workload prioritization can help. And Ariran did that presentation. And you can just allocate a certain percentage of the CPU and of the disk bandwidth for that workload. And it will protect your online workloads from being impacted. Of course, if your online workloads are not consuming everything they need, they're leaving some slack, then the full scan will happily utilize that. So conclusions. It simplifies the developer workload. You don't need to implement those full scans. You don't need to stand up a Spark cluster. It reduces the network traffic because everything is now done close to the data. And it doesn't impact your SLAs for your user-facing workloads. So overall, it's a win, except for the people who have to implement all of this.